It's a pleasure to be here today. Let me tell you a little bit about, plug that in, it'll work better. Tell you a little bit about who I am, where I come from, and why anything I have to say is something that means anything. I've been at Fermi Lab for 18 years now. It was a surprising realization when I counted that up to make the slide. I've been supporting a whole bunch of different things over there. I started out in a group that did very specific experiments and stuff. Then we moved to the central UNIX cluster. I was the guy that did the digital UNIX. The UNIX cluster had 4 different kinds of UNIX on it. That's all changed now. They all run Linux. I was also for a little while a part of the team that did development work on the Gracia grid accounting system, which is in use on Open Science Grid. I helped to do the first prototype when we were trying to figure out how that was going to work. That was pretty interesting and a place where I learned a good little bit. About 5 years ago, I joined the HPC, High Performance Parallel Computing Group, administering a bunch of high-performance clusters that are all based on InfiniBand backplanes, InfiniBand fabric. InfiniBand, if you're not familiar with it, is a host adapter card that fits on the PCI bus, and you connect a cable off the back of it that's either copper or fiber to a central switch, and it's a switched backplane then. 40 with a quad data rate that we use, you get 40 gigabytes per second duplex each way. So it's a remarkably fast way to move data and stuff between systems, which works really well in multi-processing environments when you've got a program that's on several different computers running several of the same thread, and this thread needs to talk to that thread, and it's so quick that you can even have the processor on this machine accessing the memory on this machine and crunching through things. When you add it all up into an InfiniBand cluster, that's what a lot of the supercomputers that are out there today, most of them as a matter of fact, the supercomputers are based on InfiniBand fabric. I generate a bunch of different reports. I do a lot of log monitoring and all that, but the thing that I'm here to talk about is the weekly resource accounting reports. I generate that report each week. It's presented as the first item at our weekly meeting. We look at how much of our systems have been used and who's using them. I also then end up getting in contact with the PIs, the principal investigator for each of the different groups, and I do other monitoring of compliance and stuff. So I call it resource accounting. I was interested. I looked at Wikipedia, said how would you best define resource? It's a source or supply from which a benefit is produced. Well, that's what our supercomputers are. They are a supply of computing power, and there's a lot of people that want to have access to them and use what they can. These clusters are kind of unique. It's not just a farm of batch nodes out there with the InfiniBand Connect. They have very strong power that's very, very useful. And the memory load that's on, or memory that's installed in all these and everything, it's really designed for the type of experiment that we're working with. We have several different clusters, each with specifics for the group that it supports. The majority of our equipment is in the LQCD cluster, Lattice Quantum Chromodynamics. I got a slide a little later that starts on what that is. We also have a cosmology cluster and an accelerator modeling cluster. And my department manages all of those. We also offer shared storage resources in a Luster cluster. Well, actually several, one for each of the subclusters here. We also manage the interface to data movement and storage department at Fermi. They're the ones that run our big giant SL8500 tape robot libraries. 350 petabytes of capacity at the moment. Just huge stuff. We are a tier 1 center for CERN, so much of their data that they collect, copies of it end up at our facility, and then it's paired out from there to the other researchers that want to get it. The other resource, of course, is staff, but that's outside my scope. I don't get log files that tell me who's doing how much. The word accounting, there's several different ways you can use it. There's the verb, but I'm talking about the noun It's a report or a description of an event or an experience. So you give an accounting for who's been using the computer how much. We have stakeholders that oversee and manage the funds that we use for these collaborations. They in particular are interested in getting an accounting of who's using the computer how much, where their money's going, what it's used for, and what it can accomplish. A lot of the things, when we look at the proposals, Department of Energy is a major sponsor of Fermi National Accelerator Lab. Department of Energy is also a major component of the Lattice QCD collaboration. So we want to be able to make sure that the computers were up and delivered the time that we promised. When we do the budget, we tell them we'll be able to get this many CPU cycles out of a cluster this size, and they want to see that we did that. And then we want to see, was it actually used or was it sitting idle, and who used it? And they want to see the papers and reports that come out of all of that. So the usage report that I work with all the time, and you're going to see in a lot of detail here, allows for the budgeting and planning and future projects and such to keep up with all this. So the current state of the reporting system. The reporting tools that we use today are definitely a work in progress. They're not a finished product. It seems like every month I'll come into the meeting and somebody will ask a question about the report. Do we know this or do we know that? And if it's not in my report somewhere, I have to look at where I might be able to enhance the processing of the report to add that kind of information. And part of the lesson learned we're going to talk about here is some of the things that have been added along the way to make these reports more valuable. The scope of the reporting has been revised as the requirements changed. When they moved to the new SL8500 tape robots, the tapes that were going in them are much more expensive. So a bigger part of our budget went into data storage. So we ended up having to keep track of who's using how much of the data storage, who's taking the new tapes that we have a budget for. There's a certain number of new tapes each year. So that was something that ended up being added into the report. So I'm here to tell you about the things that either became important or that we learned about as the scope of this whole thing came through, the extra resources and all that we manage. So who are my customers? The HPC department supports several, they're called massively parallel compute clusters, and they're used by these different groups. The theoretical particle physicists are my biggest group of customers. They're associated with the Lattice Quantum Chromodynamics experiment, LQCD. We're going to say LQCD from here on because I don't want to choke on all those words again. The users in this collaboration are from all over the world, from a variety of different institutions. And there are more than just the resources at Fermilab that are used by the collaborators in this institution. So the D-sub-S cluster is the one that I'm going to hit on a couple of the reports. This is in our Grid Computing Center, Computer Room C. I often give tours out at the Grid Computing Center. I installed the first 16 racks on the north end of the building, and now I manage the whole room on the south end of the building. So I got to write the book on doing tours out there. And there's also JLab, Jefferson Labs, another one of our partners, and they have their 10Q cluster, others like that. I am not in that group. I am not an astrophysicist. So I'm going to tell you a little bit about LQCD, but if you read something somewhere else, it's probably right. Why do we need HPC clusters? It was discovered, oh, let me see if the graphic's actually going to work. Ta-da. This is called a, don't do that. This is called a QCD lava lamp. They generate these all the time. The theory of quantum chromodynamics came out back in the 70s. It describes the forces involved in subatomic particles. What is it that holds the protons to the neutrons? What is it that holds the quarks together with the gluons and all of those things? And they measure all of that stuff. Now you can imagine those things are so small you can't you can't measure them by observing them. We got a lot of detectors that do a lot of things at Fermi Lab, but you can't see that small. So this work is typically done by the theoretical particle physicists, and they use simulations. Somebody comes up with a simulation, says, this is what I expect this to be. They come up with a formula or an algorithm that would represent that, and then they come to one of these large computers and they plug in a huge lattice of data. This data has, let's say there's 16 variables involved in this particular thing they're trying to test. And you need to take all 16 of those variables and try and work out all the combinations of those 16 variables. So you end up with a huge collection of data that's all got to interlink and stuff. That's why you need these massively parallel compute systems to be able to get into all of that. And the newer stuff that we've got is that much faster, and it lets us get to a whole lot more precision. And apparently it doesn't like to move forward because I did the graphic. Okay. Fermi Labs LQCD cluster is made up of several different subclusters, smaller parts. A subcluster is when we buy a set of nodes in 1 year. That set of nodes is going to be online and useful for, used to be we counted every 3 years we'd replace it. Now we're trying to get 5 years out of a cluster before we have to replace it. So each new cluster that came in has a different mix of hardware, different kind of processors, more memory or less memory, whatever, but they all use InfiniBand fabric, and they all run scientific Linux. So the JSI cluster was the one that was really big back at the beginning of all this. The JSI cluster is the one that was still being installed when I joined the group 5 years ago. At that time, it was the fastest cluster of all of the equipment that's used in lattice in LQCD. Among our lab, Jefferson Lab, Argonne, all of that. So it became the norm that we measured things against. We knew if we took this new cluster and said, this is our norm, it would be around a while, and as new clusters came in, we would find ways to come up with the ratio to mix that. I call it normalizing the CPUs. We'll see in a little bit, we talk about normalized core hours. The JSI cluster actually was decommissioned earlier this year, but it is the standard that's been in use. Okay, my presentation package. There we go. It's the standard that we still measure by. The D sub S cluster is the one that I showed you the image of before. 420 nodes, quad socket, 8-core opterons. You don't need me to read all of these numbers to you, but the D sub S cluster has got 13,000 cores in it. The B sub C cluster has got 7,000 cores in it. And the new Pi 0 cluster has 3,400 nodes in it. You notice that number keeps going down by about half, but the processing power is actually going up. These subclusters are CPU-based nodes. There's also the GPU nodes. They have the same CPU chassis underneath, but they install some number of GPU processors. The DSG, or the D sub S GPU cluster, is 76 nodes, quad socket, 8 cores, same as the machine itself, but they also now have 2 NVIDIA Telsa GPUs in them on the same InfiniBand fabric. And it is on the same backplane too, so we can move data and such from CPU nodes over to GPU nodes, all of that. It's really nice. The Pi 0 GPU clusters, there's 32 nodes in that set, dual socket, 8-core, Ivy Bridge, and each of those has 4 NVIDIA Telsa GPUs in it, in each one of those nodes. I mentioned before the online storage, that would be the Lustre cluster. LQCD has almost a petabyte of online storage in that Lustre cluster. Cosmology and their cluster has about 130 terabytes of data. And then the tape-based storage in the SL8500s. These are the numbers as of last Monday. that we have 1,617 LTO4 tapes still in the library for about 1.3 petabytes, and then 331 of these new 10KC tapes, 5 terabytes per tape. So it comes out to 1.6 petabytes of data. The SL8500s are really impressive computer or tape robots. Each one of those frames has 10,000 slots in it. So if you can fit 5 terabyte tapes in it, you can get 30 some odd petabytes out of one of these things, or 50 petabytes out of each one. There's other resources that the USQCD uses. USQCD is the name of the collaboration. LQCD is the name of the science that they do. The compute resources are spread a variety of different things. There's a big Blue Gene cluster out at Brookhaven National Lab. We've got the JSI core hours that are available at Fermi and JLab. Those all mesh together. We've got the GPU hours. There's also some, they call them leadership class computers that we have access to as part of the DOE's Insight program. We get 100 million hours out of the Cray that's at Oak Ridge National Labs, and 240 million hours out of the Blue Genes cluster over at Argonne. Lots of compute power that's used for the entire collaboration. The reporting that I do is strictly on the Fermilab equipment. The allocation committee for the collaboration gets together and develops the allocation. They list out what it's going to be that people are going to be able to use. The program year for the allocations starts on July 1st, ends on June 30th. There's 3 different kinds of allocations that they dole out: Class A, B, and C. A's are the really big ones. B's are kind of a mid-size. C are a little bitty test ones. And it talks in the slides about what it is that they're setting these up for. Allocation you can consider like a budget. Budget's a term you would expect to hear when somebody's talking accounting. The allocations are all based on normalized core hours. That's basically our currency. CPU and GPU performance, however, are like apples and oranges. You don't link them. GPUs are designed to do a very different kind of math, a different kind of processing. GPUs do vector processing. They do floating point really well and really fast. And now that we've got things like the CUDA programming language where we can write a program, write a simulation, and have it run on a graphics processing unit just like you might have a Perl program or a C program running on a CPU, they crank out a lot of good stuff. Code that you write for a GPU is written usually with a different algorithm in mind because of the different kind of math that it can do. So we really can't compare the work that you get done on GPUs to the work you get done on CPUs in a normalizing factor. So we normalize CPUs against JSI, we normalize GPUs against the D sub S cluster. They had to develop new benchmarks when they started implementing the GPUs to measure how fast these things were going. And the new Pi Zero cluster that recently went in, they had to rework the benchmarks to make it able to deal with the bigger systems. If a project gets an allocation, they would get a separate allocation for CPU time and GPU time if they're going to do both. So the existing clusters, I mentioned D sub S. We take core hours on the D sub S node and we multiply them by 1.33, and that gives us an equivalent of JSI core hours. So the D sub S nodes are about 1 1/3 times as fast as the JSI cluster. I mentioned before that there was 13,000 cores. If you multiply that by the normalizing factor, it's almost 18,000. The B sub C cluster, faster yet, 1.48 times the number of core hours, and that converts over to JSI hours again. So that's half the size, and it's almost 11, it's 10 and a half thousand core hours or cores. The new Pi 0 cluster took a whole new step, 3.14 times. So each core hour on that, you multiply by 3.14, and that's how many normalized core hours you would be charged against your allocation. So we got half as many nodes, but we still have a little bit more processing power in the new cluster. DS GPUs are the GPU that we use as standard, so that's a 1.0. The Pi 0 GPU nodes are 2.2 times that as far as the performance goes. So when we're billing against the allocation, we're billing in normalized core hours. I mentioned before that tapes are expensive and stuff, so we had to add to our systems how to bill for storage, and I'll go over a little more of this in a bit. But for a tape, we bill at 3,000 core hours per terabyte of tape storage that you're using. Now we do charge you for the whole tape. If you get one of these 5 terabyte tapes, even if it's only a little bit full, we have to go buy a tape cartridge. So you get charged the whole thing when that tape is issued to you. Disk, on the other hand, gets charged at 10 times that. So we're still working to implement this. It's been built into the allocation. It's been built into all the figuring. We're still trying to make sure we know how to best collect this, and we have to figure out, are we going to do this where once a week we see which of the groups within have how much disk space dedicated to them, and then that's what we're going to base the charge on, or do we do it once a month or what? So that's still a little bit in development. So the program year we're in right now is program year 2015. It started July 1st, a couple months ago, and it's going to end June 30th. And this year there's 270 million CPU normalized core hours and 2.8 million GPU core hours as in the allocation at Fermilab. So when there's an allocation that's issued, I get to send an email to the professor, whoever he is, so say, hello, Professor so-and-so. I set up the allocation. His allocation was issued to the name of his particular experiment. I don't understand most of these things these people do, but that describes the thing that he's actually trying to simulate, emulate, he and his coworkers. Usually you'll end up with somebody who's the PI for the experiment. He's got a bunch of postdocs and other students and stuff that are working with him and helping him run the routines. But the PI is the point of contact. So this particular experiment got issued 49.2 million core hours on CPUs and then 825,000 GPU hours. They also asked for 50 terabytes of disk space and 250 terabytes of tape. So all that was figured in when their allocation came together. And when I send him the note, I say, if you know something different, because sometimes he'll get a letter from the allocation committee that doesn't quite match the list that I got, and we straighten that out. So all he's got to do is give me a project name that they want to use in our batch system, and the list of who the users are that are allowed to consume resources within his allocation. So the reports we run today, they're based on a set of homegrown Perl and Python scripts. When I joined the group, it was all Perl scripts, and there was a guy that would sit down each week and he'd log into each one of the computers and he'd run the Perl script and it would generate output and put it in a standard file, and he'd go to the next one and use the same shared directory and add to it. I've now automated it. There's a Python script that actually goes out and does all those, log into the different machines. It used to take a couple of hours to generate 1 week's report when you had to go through and do all these things manually and make sure the files got merged in the right places. Now I can generate a whole year's worth of reports in about 5 minutes. So that's been a big help for us. So the reports tell us, summarize who's been using each cluster, specific credits and debits, year-to-date summaries of both the CPU and the GPU listings. The debits and credits come up for several different reasons, and I'll give more detail a little bit later, but the gist of it is there's credits for reduced performance during a load shed event, debits for storage, tape and disk stuff, credits for a job that's failed and it wasn't, I don't want to say it wasn't the user's fault, but the job finishes, it thinks successfully, so it ends up with generating a billing record, and I charge them for it. If we find out later that there was some corruption in some memory card or something, and he's got to throw that data away, we'll give him a credit for that job, and he gets that time back. And then there's the problem of what do you do when you've got dedicated nodes set aside for a project. You don't bill based on how long did the job run, you bill on how long was that set of nodes dedicated for that user. So this is the part of the report for just one cluster, in this case the B sub C cluster. It's a week's worth of data. The week always starts on a Tuesday and ends on a Monday. So at midnight, the end of Monday, any log files that are up to date, those are the records I read to generate the report. The B sub Z cluster in this particular instance was one that was billable. When we installed the Pi Zero cluster, we had to run benchmarks, we ran burn-in tests, we ran a whole bunch of stuff against it, but none of that got billed to any particular user. After we had gone through and done the benchmarks and then done some of the burn-in testing, we invited what we call friendly users. And we have users that are experienced with all these different clusters, and we let them run a few of their simulations on the new cluster and see how they're going to perform and what kind of changes they might need to make in order for it to be compatible with the architecture on the new cluster. I'm going to go into all this color coding and everything on some slides that are coming up, so I'm going to skip over that at the moment. This is the shorter report that comes out for the GPU cluster. So these are the project names. The projects that did it, the Lattice SUSY GPU group ran 161 jobs. It was 1.1K normalized core hours. It was 5.2% of all the work that got done this week on that cluster. These guys got 94% of it. They were just, had that many jobs in the queue and were there for it. The fact that it was only 88% busy for the entire cluster tells us there was some idle time. So if somebody wasn't to go in and flood the queue with all their jobs, they're all going to get to run. They're not working to see who else they have to fight for priority. When you've got idle nodes, you go real far, real fast. This is the part of the report where they go over the specific debits and credits. At the beginning of the month, so October 1st fell within this week. So on October 1st, the first quarter of the program year, these groups were using tapes to the point where these were the charges that were run against their accounts. That goes up and takes a little bit off of their allocation, their usage. It's a separate part of the report. There's a lot of weeks where this part of the report comes up and says there was no debits or credits this week. We didn't have anything exceptional or whatever. But I made sure I grabbed the October 1st one because it had a good example in it. So this is the big report. I don't expect you to be able to read this. I'm going to break it out and go over it in little pieces. This part in the middle here is where all the projects between Fermi and user test in the alphabet, I just took them out so that we'd be able to read this thing. But we're going to look at this in several pieces. I'll explain this little part up at the top. We'll look at the weekly information, then we'll look at the allocation area in the middle, and then we'll look at program year to date, the numbers on the far end. And then at the end, we'll go through those same three areas for the summary part at the bottom. So here's what was at the top of that report, blown up a little bit bigger. At this point in the year, this report was generated on October 21st. We were 36.1 weeks remaining in the program year, which means we're 30% done with the program year. Burn rates that we'll see in the charts below are expressed in a number of weeks. It's basically a key, explains what's coming up in the parts that follow. What the year-to-date columns mean and total normalized. The only thing in there that's really significant is the fact that there's total normalized and then there's program year-to-date. The total includes the non-billable stuff, so we can show that we had a system up, we provided a resource, we just weren't billing anybody in particular for that. So this is the big report again. We're going to move up to this part right here where we look at weekly. The left side of this summary here handles all the weekly stuff. These are projects that ran through. the number of jobs that that project processed in a week. So one thing I can tell you from the color coding, if it's gray, that means that particular project was idle that week. They did not use any resources. They did not run any billable jobs. So in this case, the BSM group ran a little bit, DM Pol ran a little bit. The part that ran the most was, in this case, happened to be the one that was cut out. But each group, we get a report, how much did they use, how far did they get. And I've included on the end of that the allocation column. I wanted to show you that if they used this many hours, what they used was 3.8% of their total year's allocation. So it's helpful for them to see how much allocation they're burning each week, or at least in a particular week. Those numbers always vary. It's not a consistent thing, so in the first couple of months they may be developing their code and they're not running a whole lot of jobs. Somebody else may be preparing to do a paper in October, so he's going to be running like very heavily very early on in the year. An example is B Meson Dist. It's in red because they have already used up everything that was in their allocation, and any additional computing that they do from here on is running opportunistically. So they're sneaking in what they can. This is the allocation portion that's in the middle there. So we can see that B Meson Dist here had 15,000 hours allocated, and they've already used 103,000 hours this year, which means that they've been very effective. They've worked 793% of their allocation. It's opportunistic running. When the machine's idle, somebody else can run something. If there's people that want to run things that still have allocation left, these guys get 0 because their priority's set lower. So that's this part. And then the last part on the end is the program year-to-date figures. So there's B Meson Dist again, that's how far they got. They ran this many jobs so far in the program year for this many allocated hours and that many normalized total hours. At this point, there wasn't anything running on that cluster that was not billable, so everything comes up showing as billable. Lesson number 1, I didn't really have a slide that said it. Lesson number 1 that we had was that we needed to normalize our core hours. You know, everything's got to be in one common unit. Lesson number 2 is that we have to adjust batch priorities. When we get to an experiment that has used up its allocation, in this particular week of the report, the Charmonium experiment crossed over, and I'll show it to you on the summary report that's coming up. I go into the configuration files for the batch manager. I change their priority to a negative priority, and that lets everybody else's jobs get at the system first unless there's idle time, and then these guys can go ahead and run. So that's this opportunistic running that I've mentioned. There are occasions where we may need to increase somebody's priority. If they've got a paper coming up and they've got a lot of processing they got to do, we'll tell them we'll up their priority for a couple of weeks. Everybody does that kind of stuff. In some cases, they need so much processing that we have to dedicate some number of nodes, in which case they're the only person that can use them, and they get charged 100% for that time. So when I said Charmonium reached their budget, that's the reason for this color out here. That says that this week they reached their allocation. So they had this many hours they processed in the week, and that put them that far over their allocation. So the red is somebody that's already reached and used all of their allocation, and now we're starting to show in negative numbers what they're accumulating. So the summary part down in the bottom, again, it's got a weekly thing. I can say that this week there was this many normalized core hours available across all of the clusters in that Lattice QCD group. There was this many hours that were actually consumed by people, which means that that cluster was only 56, or that these systems were only 56% busy. That happened to be a week that we had a maintenance work done by the Commonwealth Edison, the power company. Twice a year they have to come through and tighten up all the connections where the power comes in, because with the heating and cooling that they go through, they tend to get loose, and that's a very bad thing. The part in the middle talks about allocation again. So this is how many allocated hours have come up already this week. This is how much is out there. This is how much is still left in the program year based on what's been used so far. And then there's the year-to-date summary. We've used 24% of the allocation, but like we said before, we're 30% of the way through the program year. That was one of the numbers from back up in the top. And there's very little difference between the billable and non-billable on this particular report. So again, there's the detail in the 3 different sections. There's the summary in the 3 different sections. Color codes here. The yellow, those are unallocated accounts. User test is an account that almost anybody can submit a job to. It actually has a very high priority, but it has a very small limit on the number of nodes you can access. And people will submit a job there who've been put on the list of people allowed, and away it goes. But it has no allocation. So there's no real limit. There's no adjusting priorities unless we start seeing problems somewhere. So that's the yellow is the unallocated. The red, of course, is the over. The orange there is what has just recently gone over. Class C allocations, so I told you those were the really small ones. You'll notice each one of these that's in green is a Class C, and each one has the same 80,000 hours allocated to it. On the CPU cluster, that's what a Class C address gets, is 80,000 hours. And it's usually over a period of 6 months. And they'll run their test jobs and see where they can get. The gray, again, is the inactive here. I put one on here to make it easier when I'm giving the report. It's interesting. It's the one that's, these guys had at least 20% of that report there. That's why they've been highlighted in the interesting. These guys had over 20% of the number of jobs that went, but their jobs were smaller, so they really didn't use that big a chunk of the processing power. Credits for failed job, I mentioned that earlier. They would show up like this, and I even list the job number that it was credited against. Credits for reduced performance. These load sheds we talk about, we have times in July where Chicago gets incredibly warm, and the cooling towers that are out in back of the building can't keep up with shedding the heat fast enough. So we have to generate less heat. We end up going in and turning down the priority or turning off bunches of nodes. When you turn down the clock speed in the nodes so they're not burning quite as hot, they don't perform as well, and we need to make adjustments to the ratio for how much we're billing. So writing these kinds of credits was another thing we learned how to do and learned the importance of doing. And the other thing we do is we up the wall time limit at the beginning of a load shed. So if you had a job in that had a 24-hour wall time limit, we'll bump it up to 36 hours during the load shed because it's going to take you longer to finish your job. Burn rates. It's the one part of the report I hadn't really explained to you yet. Burn rate means that these guys used only 0.2%, and it's going to take more than 36 weeks, that's the number of weeks left in the year for this particular date range, for them to burn the whole thing up. BSM, however, used almost 4% of their allocation. And if they continue to run at the rate they ran this week, they would use up the rest of their allocation in 19.2 weeks. That's a little early for some of the papers you're going to have done at the end of the year, but that's just this week. If you actually look at their year-to-date average, basically, it's still going to take them more than 36 weeks. They were running much faster this week than they have been before. These guys, Fermi, Milk, Heavy, Light, were running slower than they used to before. They're not going to finish if they keep running at that rate. But remember, we were 30.6% of the way through the year. They're 34% of the way through their allocation. They will finish in 30.3 weeks, and there's 32 weeks left in the program year. They're right on track. They are also one of the largest allocations that's out there, so they're the ones that need to watch that stuff most closely. All right, let me summarize the lessons learned, things that we came across as we went through this. We have to normalize core hours. We use a standard across all the different facilities. anybody that gets an allocation at JLab on the 10Q, their hours are even normalized to our JSI core hour. That is the standard for the US QCD collaboration. Next year, since JSI has been decommissioned, we may have to pick a new standard. CPUs and GPUs have to be treated differently. They truly are apples and oranges. You can't have a factor that's going to tell you if I can do twice as much stuff on a GPU node as I can on a CPU, because it depends on the code. And we had to add charges in here for storage, so we had to figure out some number of core hours we would charge for a tape or for disk. It all comes down to the budget, what it costs us to do it. We make adjustments to batch priorities so that everybody gets a fair share. We reduce the priority for a particular group when they're over their allocation, or if they're unallocated, they have a lower priority. We increase priorities as needed. When you're dedicating nodes, that of course is, you're the only thing that has priority on that set of nodes. Charging for dedicated nodes gets interesting. When the job goes through, or the report goes through, it looks at all the log records and it says these jobs finished. Well, it's going to have records that Fermi, Milk, Heavy, Light finished this many jobs and they used this many hours. But if I had dedicated nodes and they let them sit idle for 2 days, I still have to charge them for those 2 days of idle time because those nodes were dedicated. They're theirs to use and nobody else's. So we charge them for the full 100% of the time, which gets tricky if you're doing all your math based on log records. You have to say, well, the ones that happened in the dedicated don't get added into the math, but then I have to add in, here's the dedicated charge. We've learned about doing credits for not only failed jobs, but the load shed. Load shed's only something that started happening about maybe 4 years ago. It's been a bane to us, but when we added some of the latest stuff to the building, we actually reached the thermal capacity of the building, our ability to keep it cool. And load shed events are driven by Mother Nature. I get a notice from the nice folks over in facilities that there's a chance we're going to have to do this. If they send us the page that says implement load shed, we have a short number of hours to turn off certain nodes, power or reduce the consumption on other nodes so that we don't overheat the building and shut the whole thing down. And then it became very useful to do burn rates. The concept of burn rates came up one week when I was presenting the report, and one of the guys that was in the room was part of one of the projects, and he said, but are we going to use it all up by the end of the year? We hadn't figured that before, so that was a later addition to the reporting. So that's what I bring to the table, the things we've learned along the way. We haven't solved all the problems. I don't have all the answers. The report is not done. It's going to keep getting better over the years. We're working right now to implement, and there's a Postgres database that's collecting all the log file records, and then I can do a lot different reporting if I can pull out the log records from the Postgres database. Right now, when I rerun the set of scripts for the year, I go out and read all those log files from all those batch processors. It works. I'm not complaining. But if a user wants to say to me, how far have I used my allocation right now with the database, I could run a quick query and tell you. So that's why we're migrating toward the database. I appreciate your patience with me. I've got a bit of a hearing loss, so if you've got a question, I'm going to ask nicely that you make sure you get to the microphone. I'll take whatever questions you might have. I'm here all week. Find me in the hall if you like to, or I can show you actually samples of some of the reports. That was just a sample photo they gave me when they said, here's the Fermilab template for PowerPoint slides. And I thought it was a really cool picture, so I figured I'd end on that.
Hi, Ken, thanks. Just one question. You mentioned that here relatively recently you've been doing those burn rate reports. I was wondering if you'd thought any more about providing your principal investigators a more graphical view of what they've been doing over time, maybe provide them, time series metrics kind of things, if that's something you are looking at.
That's something that's been discussed. The guy that actually developed our database prototype, he's a SQL wizard. And all of his stuff he writes in bash shells and here documents and does amazing things with a single command line thing. One of the ones that he generated was for my supervisor, who said, I run this job and I need to see how well it uses. And it actually generates a histogram on his VDT terminal, whatever, on his screen, and it shows him the processing that happened through the course of that job. It's pretty unique the way he did it. But yes, it would be valuable to do that. One thing that I won't say I'm proud of it. I'm a little, maybe even concerned about it. This report that we generate each week is shared among those of us that administer the systems. If you are a user on the Fermi Milk Heavy Light project, you can't go look at this report and see what the users on the Charmonium project have been doing. The summary of this report with everybody's data on it is discussed in our group meeting. If a user wants to ask about their particular thing, I can provide them that individual information, or they can run a command line query that'll come back and tell them this is how far you've gotten. Sir?
Yeah. How do you decide on a cluster factor?
The cluster factors are determined by benchmarks. We have 3 different programs that we use. They are all actually simulation type programs that have been used in the past on the cluster. Some of them are smaller, some of them are larger. They do different kinds of math, so there's a different mix of floating point versus other things. So there's 3 benchmarks we run, and they all get merged together to come up with a performance number for that cluster. And then we compare them at the end and we say that performed this much faster than the JSI cluster did. So those numbers come out of 3 benchmarks that get worked together. On the GPU nodes, there's, I think, just 2 benchmarks that they use. It's a whole different kind of processing, but it's the same idea. We merge the 2 benchmarks, get our statistics, and build from there. You're welcome.
Hi there. I apologize, I missed the first couple of minutes of the talk, but are you aware of Platform's analytics software that does a lot of the LSF analytics by user, by project, and so forth? We use this at Sanger, and we tie this into Tableau so that we've got graphical reporting that the users can see. So instead of coming to us with the pitchforks and the flaming torches, they go to each other with the pitchforks and flaming torches, which works actually rather well. But it's interesting to know if you'd used that or whether you explicitly decided not to use that software when writing your own.
Well, like I said, the report that I generate is actually something that's used in-house among the administrators. It's not something that goes out in front of the users. We're looking for better ways to present that. We do, at a certain point in the year, send each principal investigator a status update that says, here's how much of your allocation you've used so far to date. We don't do anything much fancier than that. If they want to find out, there is actually a command line that they can run. It's called quota. They run that on their system, and it says for each of the projects that this particular user is associated with, this is the percentage of the quota for that project that you've used. The quota command goes against the data file that sits underneath this report of mine. So when you run an quota command on Thursday, what you're getting is, as of midnight last Monday, this was how much you had used. When we move into the database, and we've already prototyped it, you type an quota command, it actually does a query into the database, and it comes up and says, right now, this is where you're at. We haven't had any call for yet. It would probably be quite interesting to see if we could show patterns of usage and provide that kind of extra information for people.